make up the power set. Note that while this set has 3 elements, its power set has 2 cube equal to 8 elements. You see, 1, 2, 3, 4, 5, 6, 7, 8. So it seems that if we raise 2 to the power where the exponent is the cardinality of this set, then we get the cardinality of the power set. That is actually true in general, and we will prove this also in the 6th section. And this is the reason we have this notation. This gives us a hint as to why we denote the power set of x by this notation, 2 to the power x. Actually, I should not say 2 to the power x, but it just looks like that. We will return to this issue not just in the 6th section of this chapter, but in chapter 8. Okay, so now we have gathered 10 axioms for set theory, but for the sake of completeness, let us just introduce one more axiom. A new axiom known as the Axiom of Union. This allows us to take unions of a large number of sets. You see, so far we have seen the axiom of pairwise union, which allows us to take the union of 2 sets, and then with the help of induction we can enlarge it to the union of any finite number of sets. But keep in mind, we discussed it previously, we still have no what can I say, no axiom that allows us to take the union of n sets where n is any natural number. We can of course take a specific value of n and apply the axiom of pairwise union again and again to be able to say that this is a set, a legitimate set. However, we cannot write n here. That is still not available to us. So to rectify that mistake, or to be able to do so, we now need a new axiom, which we are going to say the axiom of union. Okay, so this is the 11th axiom. Union, and this one says, let A be a set all of whose elements are themselves sets. All of whose elements are themselves sets, then there exists a set which we denote by this symbol. Okay, consisting precisely of the elements of a. It may be confusing at first, but we will decode this, we will figure out this. Okay, so what we are saying here is that we are given a set A, okay, whose elements are all sets. There may be more. Then there exists a set whose elements are precisely the elements of the elements of A. These are the elements of A, right? All of them are sets. They also contain some elements. So you take all these inner elements, collect them, and make up a set. That is this set. So this set consists of the elements of A. So with this understanding, what can we say about this union? Are we calling this something? We haven't said yet what it will be called. Anyway, thus for any object X belongs to the union of A if and only if X belongs to S for some S belonging to A. That is, an object will be an element of this union if and only if the object is an element of some set which itself is an element of this collection A. Still it may be confusing, so let us take an example which will make it more clear. It's actually nothing that difficult. The thing is that in mathematics, since we have to formally present a definition in the most general form possible, in the most general style, so sometimes looking at a definition we will not immediately get it. Only after looking at several examples we get the idea. So there is no need to be afraid of a definition, we just have to figure it out. So here is the example. We can take any example, but let us just take the one Tao has taken. If A is equal to 3 5 2 3 3 4 and 4 5. So you see here A is a set whose elements are all sets. A has 3 elements, each of them is a set. Then union of A is equal to 2 3 4 5. It's just like this. You have gone to the market and you have come back buying some stuff. You have some bags with you. Each bag has some objects inside of it. So these are the bags, and this inside there are objects, food items or whatever. You dump all of them, empty all the bags, and you mix all the stuff together. The final set of all the stuffs is your union. That's all. Okay, you see one thing, that these sets are, okay, no, they are not disjoint. So Tao has been careful to take this example. Okay, so unlike the real world example of having stuff inside bags, here some object may belong to both the bags, which however in reality is not possible, but just to just to give you an analogy. Okay, so this is the set. Now there are some remarks. The axiom of union that means this axiom combined with the axiom of pair sets, that one you remember, axiom of singleton sets and pair sets, gives us the axiom of pairwise union. We have already seen this type of things happening before. We have also mentioned in the beginning itself that the list of axioms that we have accumulated, that is an overcomplete list. It may be the case, and it is the case, that some of the axioms are consequences of other axioms. So for example, here if we combine the axiom of union, which we have now seen, with the axiom of pair sets, then we get the axiom of pairwise union as a consequence. One more thing, one more consequence of the axiom of union is this. Let I be a set, and for each element alpha in I, there exists a set A alpha. Okay, so there is a set I, and for every element alpha in I, there exists a set A alpha. Then we can define the union of A alpha as alpha varies over I to be this set. Okay, let us see what this set is actually. First of all, we have the set I. Now from I we collect elements alpha. Each time we collect an element alpha, we get a set A alpha. Okay, we collect all the A alphas together, we get a set. For that set, we are forming the union, and we are denoting the union by this. How is this a set? Let us just see that. First of all, for every element alpha in I, there is a set A alpha. So by the axiom of replacement, this set, neglect the union, okay, this collection whose elements are the sets A alpha, this collection is a set by the axiom of replacement. Since this is a set whose elements are themselves sets, so this collection is just like this A. So the union of its elements, that is the sets inside, can be taken according to the axiom of union, and that will be a set. So that's how this is a set. And I think we have mentioned this. Yes, which is a set thanks to the axiom of replacement and the axiom of union. And this idea can be understood with an example more clearly. For instance, let not alpha, let I be the set consisting of these three elements 1, 2 and 3. A1 be the set, we are just going to take this one, okay, 2, 3. A2 be the set 3, 4, and A3 be the set 4, 5. So you see that for each element in capital I, there exists a set. For 1 we have A1, for 2 we have A2, for 3 we have A3. Then union of AI, or since we are writing alpha, so let's just write alpha, although they are the same thing. In this case is nothing but this set. Okay. Note that, but before we write this, I think in this situation there are so many things, it's difficult to remember everything. In this situation, we call I an index set and elements alpha belonging to I as indices or labels. It's like we have the sets here and I is a set of labels or tags or names that we are giving to these sets to distinguish them. That's how we should perceive it. Okay, so as indices or labels, the sets A alpha are thought of as labeled by alpha belonging to I and they form a family of sets and indexed family. Okay, note that X belongs to this union if and only if X belongs to A alpha for some alpha belonging to I. You compare this condition with the similar one that we previously had for this one. Okay, let me just write it here. X belongs to union of A, where you should keep in mind that this A is the collection whose elements are sets in the context of that thing. Okay, axiom of union. If and only if X belongs to S for some S belonging to A. These two situations are not very different. The only thing is that the sets S that are elements in A here are nameless or labelless. So that means X belongs to this union if and only if X belongs to at least one set in this set. Here that same thing is being said, only now since the sets have labels, we are, instead of saying about the set itself, we are bringing the label for some label alpha in I. That's all. It may feel overwhelming in the beginning when we see these things, but the more we work with them, the more familiar they get and the more we are comfortable with them, and the easier they get also. Okay, there is one more point. Note that while defining these things, that is the index set and all these things, we haven't said anything about whether I is non-empty or not. You may think that having an empty index set is foolish. Yes, it may be foolish or it may be useless, but it's not wrong. You see, when we say that for every alpha belonging to I, there exists a set A alpha. This statement makes sense even when I is empty. You see, this statement is actually an implication. You have to keep that in mind. What it says is that if alpha belongs to I, then that implies A alpha is, or rather I should write like this. There exists a set A alpha. Now if I have empty set in place of I, is this statement true? It is true. By now you know, because you see the hypothesis of this statement is false. So regardless of what the conclusion is, the statement is vacuously true. So there is no problem with this statement. For an empty index set also we have a collection of sets. And so that means we can have the empty set to be the index set. But what happens to the union in that case? Note that the union of A alpha, alpha belongs to the empty set, is actually empty. And the question is why? This, however, I will not answer. I want you to think about this, why this is empty. Okay, so this is about union, the axiom of union, and some consequences of that. Now, just like that, we can define intersection of any such collection of sets. Just like the union of an indexed family of sets, we can define intersection, but there is a condition, provided the index set is non-empty. If the index set is empty and you try to define an intersection, which I may write like this, then there are some peculiar problems that appear to, since we will never need this type of thing. So in this case, we restrict the index set to be non-empty in case of intersection of an indexed family of sets. Okay, however, and the definition goes like this. So let me just write it in a separate paragraph. Let I be a non-empty set and for each alpha belonging to I, let A alpha be a set. Okay, something else has come to my mind at this point. Note that although we are saying that the index set is non-empty, the sets, these sets A alpha need not be non-empty. They may be empty. All of them may be empty also. We are not concerned about the emptiness or non-emptiness of the sets themselves of which we are taking union or intersection. We are concerned about the non-emptiness of the index set, the set of labels. There should be some labels. Okay, be a set. Then we define the intersection A alpha belonging to I by first choosing some index beta belonging to I, and this we can do because now I is non-empty. So by a previous result which we named as the single choice, from a non-empty set we can choose one element. This is possible because I is non-empty. By first choosing some index this and then defining like this, which I will write here. Intersection of A alpha as alpha varies over I is defined to be the set of those elements in A beta such that X belongs to A alpha for all alpha belonging to I. Okay. When we defined the union of an indexed family, the fact that it is a set followed from the axiom of replacement and the new axiom of union. However, what makes sure that this is a set? I mean, what ensures that this is a set? This is a legitimate set. You can see that this follows from the axiom of specification, because according to our definition, the intersection is a subset of A beta. But what subset? It consists of those elements that belong to not just A beta but every A alpha for alpha belonging to I. So, note that axiom of specification ensures that this is a set. Set means a well-defined legitimate set. Now there may be one problem with this definition. It may seem that this definition depends on the choice of beta. You see, what we are doing, first we are choosing an index beta in I, but how we are choosing beta, that we don't have any instruction about that. We are just arbitrarily choosing any beta from I, and we are defining this to be like this. So isn't it obvious that this definition depends on beta? So if I choose one value of beta, if someone else chooses some other value of beta, we may apparently get two different values of this intersection. Actually, that is not the case. We will end up with the same set, and that is one exercise. It may seem that the above definition depends on our choice of beta. However, it does not. That is, whatever beta we choose in I, we end up with the same set. And this is exercise 9. And just like union, let us write a condition for an object to be an element of such an intersection. Observe that for any object x belongs to this intersection, alpha belonging to I, if and only if x belongs to A alpha for all alpha belonging to I. Okay. And lastly, there is one remark. With this section ends, I mean the text part ends.